Okay, we are continuing our discussion of what's called optimization. And let me go ahead and try to spell that. Optimization. There it is. So in optimization, we're basically utilizing the first derivative test. We're trying to find the minimum or the maximum of something. All right. Now, in this case, what we're going to do is we're going to review a problem-solving process for optimization problems. And the first thing we should do is, of course, read the problem. Secondly, we should draw a picture. Third, we should use meaningful variable names. All right. Then we write some kind of equation that relates the variables. We find any kind of critical points by taking the derivative, either setting it equal to 0 or finding where it's undefined. And then lastly, we apply the first derivative test to find the minimum or the maximum values. And of course, wrapping it all up, you kind of have to back substitute and find what it is that you're missing. Okay, so let's take a look at this example, and we'll look at one more after this. And this is a classic problem. It says find the dimensions that produce the maximum floor area for a one-story house that is rectangular in shape and has a perimeter of 159 feet. So we've got the perimeter here. They want us to find the maximum area. So it's rectangular. We know we're going to utilize a function. We're going to call it A, which is the length times the width. And I know the perimeter P is 159. And I also know that perimeter is 2 times the length plus 2 times the width. And so I'm going to say, well, 159 then equals 2L plus 2W. And then I'm going to go ahead and I'm going to solve for one of my variables. So let's pretend or suppose that I want to solve for the variable W. So then I'm going to write, let's see here, 159 minus 2L equals 2W. And then I can go ahead and divide everything by 2. And I do it just like that. So in the end, my width formula, W equals 159 over 2 minus L. And so now that I've got this right here, this is the function that I want to optimize and take the derivative of. So I'm going to then find, let's see here. Actually, no, this is not what I want to find the derivative of. This is what I want to back substitute into the area formula because I'm trying to optimize or maximize, in this case, the area. So I'm going to take this and I'm going to plug it in right here. And I'm going to say A, the area, equals the length L times 159 over 2 minus L. And so I distribute the L. I get 159 over 2L minus L squared. And this is my formula A for my area that I want to maximize. And I take the derivative. 159 over 2L just becomes 159 over 2 minus the derivative of L squared is 2L. Okay. Now what I do is I set this equal to 0. And once I've done that, okay, I get something that looks like this. In this case, 2L equals 159 over 2. So then I divide both sides by 2, which is the same as multiplying by 1/2. And I get L equals 159 over 4. 159 over 4. All right, now that I know what L equals, I can use a calculator, or this is actually not too bad. It's 39.75, okay? So this will help us when we are doing our first derivative test. So let me go ahead and draw my wiggle graph here for A prime. I want to verify that this 39.75 is going to give me the maximal area. If that's the case, my derivative should go from positive to negative. So what I'm going to do is I'm going to plug in numbers right in here for L, something before 39.75. Let's suppose 0 is a good test point. And then after that, I could pick something like 40. All right. Well, it turns out that yes, this is positive and this is negative. So this does give me a maximal area if I use this right here, this dimension. So now that I've used that, I can go in and plug in this 3975 into my perimeter formula, or really my width formula. So I'm going to take it and I'm going to plug it in right in there. Okay. And so when I do that, I get W, and let me change my pen here. Okay. I get W equals 159 over 2 minus 3975, and what you end up getting is 39.75 exactly. So it's an interesting problem here, because what we end up finding is that for this what was it, rectangular floor, all right, it actually, to have the maximal area, should be a square. So really interesting. So let's go ahead and write that out. The fact that the length should equal 39.75 and the units are feet, and the width should equal 39.75 feet as well. So it should be the maximal area of this rectangle then should be really the shape of a square. All right. So I think we've got one more problem here that we can look at, and the process is very similar. All right. So let me go ahead and take a look at that one, and I need to move this problem, save it for another video, out of the way. Let's see here, right about there. All right, there we go. So here's number 4. It says an architect needs to design a rectangular room with an area of 67 square feet. Okay, here we are again with this rectangular room problem, or rectangular area. I'm going to say, my guess is that it's probably going to be a square that will maximize, or in this case, minimize the perimeter. So let's go ahead and take a look at that. This one's a little bit different. All right. We know that the area is equal to the length times the width. That's important. We know that the area is going to be 67 feet. All right. So let's go ahead and draw a picture here. Here's this rectangle. My area equals 67 square feet. I know that this is, suppose, the length, and this is the width. All right. So I've drawn my picture. The other thing that I know, and I'm going to write this out again, 67 equals the length times the width. I know that the perimeter 2L is equal to 2L plus 2W. All right. I've got that down. So now that I've got that, I'm going to use my formula here, and suppose that I say with this formula that I initially had for area, I say that the width W equals 67 divided by L. Well, this is interesting. I'm going to take it and substitute in for my perimeter, and I've created a scenario where I actually have a derivative, or I'm going to have to take a derivative. Maybe that's not necessarily difficult, but it's just a little bit different than what we maybe have seen so far, but that's okay. All right, I get something that looks like this, 2 times 67 over L, and so I get 2L plus, and then that becomes 134 divided by L, and this is the function then that I need to optimize and find P prime. So derivative of 2L is 2, but then I have to rethink this formula for perimeter to say that it's 2L plus 134 L to the negative 1. All right. So when I do that, I'm going to actually take the derivative, power down, so it becomes negative 134, and L to the minus 2, because you subtract 1. Okay, so what does that look like? 2 plus, well, that's actually minus 134 over L squared. And I set this equal to 0. And now that I've set it equal to 0, I can write it out like this, and then I just have to kind of crisscross here. I can say then that L squared equals 134 divided by 2. All right, and I know that that goes in evenly. Okay, I'm sorry, not divided by 2. Oh yeah, it is divided by 2. Sorry, I don't know what I was thinking there for a second. And I get something that looks like this. L squared equal 67. So to find L, I take the square root. So L will equal the square root of 67. Now you can take this and back substitute, but what you're going to find is that if the area is 67 units, the length will have to then be squared in order to get a 67 period. So you can back substitute it, like I said, you can back substitute your L right back in over here, and you're going to get 67 equals square root of 67 over W, but then you solve all that good stuff and you end up with another square root of 67. Okay, so in that case, we could do something simple. We could just take the square root. It's something like 8.19. All right, but now that you've found that, you say 67 equals 8.19 divided by, or times W. You divide both sides by 819, and you get W equal 8.19. All right, well, we haven't even tested if that is optimal, so what we're going to do next is test it, but at least now we've got the length and the width. Okay, so I'm going to plug 8.19 here. I've got it right there, and then I pick numbers before and after in my P prime formula here, which was this one over here. There's my P prime formula. You pick a number before 8.19. Let's see, you get a negative number, but if you pick something after 8.19, you get a positive. So this right here, because it goes from negative to positive, will minimize the perimeter. It is a minimum. All right, and so we end up finding then that the length is going to be 8.19, whereas also the width is also 8.19. So this rectangular room actually needs to be a square. All right, so something just kind of keep in mind there, because I did mention it earlier. All right, but I hope these two sets of problems were helpful. All right, you might want to rewatch them. So hopefully you get the hang of it. All right, but remember, as always, like and subscribe.